Hello, hello. Yeah. So, good evening, everyone. So, today we are going to start the first live session of transport phenomena in biological systems. So, myself, Srijita. I am from IIT Guwahati, fourth year PhD student. So, we'll wait for 1 more minute and we'll start. So, let's start. I will share my screen first. I think my screen is visible. Yeah. Yes. So, here, so in the first lecture,
Hi, Srijita.
yes.
Yeah, so I'm the TA for this course.
Okay.
Like actually, there is no student have joined for the meeting. I think so.
Yes, yes.
Um, do we still need to run this section? No, I'm not sure
Yes.
about it.
Because like I have been doing this PMRFTs since last 2 years, so these are like these subjects
Yeah.
are a little bit tough, so people mostly don't join. But we have gotten the instruction that we should be completing the like the
Complete.
session.
Okay. Okay.
Yes, so
Uh,
we will upload this lecture in the YouTube afterwards. So they
okay,
will
fine.
look into that. Yeah,
Okay, then you can continue the section.
yeah, yeah.
Fine.
Okay.
Do I need to stay back or is that fine? Only you can be there.
Yes, yes, yes. I can only teach only. Yeah, no need to stay.
Oh, okay, fine.
Yeah,
Okay, thank you.
yeah, yeah. Okay, sure. Yeah. So let's start. So here, what happens in this course, in the first lecture, or in this session, in this week of teaching, Sir has mostly introduced you about the transport phenomena, like what is transport phenomena and how can it be applied to the biological systems, right? So what is transport phenomena? Basically, transport phenomena is a core subject of chemical engineering department. The people, if you are doing chemical engineering, you must be going through this course probably in third year or fourth year. So it's a very, very important subject because transport. Okay, so transport phenomena is a subject which like amalgamates all the basic fluid dynamics, heat transfer, and mass transfer. That means in our everyday life, everything, every system, every processes, every reaction is part of this fluid mechanics and the heat transfer and mass transfer. Everywhere it takes place, right? So similarly, in the biological system also, that means in our body, if you can think of, in our body also, if you think there is always a fluid, right? So our body works on the basis of this fluid dynamics mechanism at a very nano scale, or we can say micro scale, right? So inside our body, there is also heat transfer is happening, mass transfer is happening, the food is going from one organ to another organ. So that is also the one kind of transfer. Then the concentration, diffusion, all these things happening in our body is part of this transport phenomena. So it is basically a very important subject, and generally in the chemical engineering course we do it for macro scale systems, but here in this course we'll be applying this to the biological system. So in this week, the content of this week is very basic, right? Like what is flux, what is rate, what is the mass flow rate, and this type of things are being taught here in this first week. So I'll be going through in the basic level, and as we progress, we'll learn the different things of this transport phenomenon. Okay, so first, if you remember, Sir has mostly talked about the continuum domain, right? So first we'll revise the content of this topic and then we'll do assignments, okay, and some extra mathematical problems, which will be helping you for solving this week's assignment. Okay. So what does mean by continuum domain? If you have gone through the lectures, you can definitely tell that what is continuum. Right. So here the fluid or whatever our system is considered as a continuous system. Here our system is considered as continuous system. That means there is no discretion. That means we are not considering each molecule of a system. Suppose this is our system and it consists of different molecules. So we are not thinking the system on the molecular basis. Rather, we are thinking that the whole system is a continuous system. That means there is, in the continuous system, we are supposing that there is no molecular spacing, and we are, so there is no molecular spacing. All the atomic aspects, sorry, all the atomic aspects are negative or removed. So, if you think with the if you think in a with the graph, so this portion is the continuum portion, and beyond this portion there is discretion. If you remember the graph, so this portion is the molecular property portion, which we are not considering in this course. This portion is the molecular property. Okay. The length scale of this area is very small. Okay. Length scale is small. Okay. But in this case, size is intermediate. So, generally we consider L as the characteristic length of a system. Characteristic length, and lambda is our mean free path. Do you know the mean free path? Can you tell me? What does it mean by mean free path? Can you tell me what is mean free path? Yes.
The average distance.
Yes, average distance between two molecules before the colliding. Okay, when two molecules collide with each other, the distance they covered before colliding is called the mean free path. So, in the continuum approach, the characteristic dimension, that is L, is greater than the mean free path. Okay. So in the case we'll be discussing in this course, all cases will be in this continuum region, because all here the characteristic length will be higher or greater than the mean free path between the two molecules. Okay. Beyond that, we are not discussing in this course. First, if you have gone through the lectures, first sir has talked about the flux. So what is flux? Flux is the quantity, any quantity it can be. Okay, so it can be mass, it can be volume, it can be charge. Okay, any basic parameter per unit time and per unit area. Suppose there is a door, or you can say there is a pipe and fluid is passing from here. So what is the mass flux? It is the volume mass flux will be the mass of this material passing through this area per unit time. This definition is mass flux. If it is volume flux, then it will be how much volume the fluid contains per unit area and per unit time. So this is the flux. Then comes the rate. So what is rate? Flux, we have seen that flux tells about per unit time and per unit area quantity. But rate is defined per time, right? So mass flow rate is that kg per second. That means suppose mass flow rate, or you can say in define like quantity, whatever be the quantity per unit time. This is defined as rate. Rarely we tell that a car goes with a speed of suppose 50 km per hour. So we tell it as velocity, but the rate also possesses the same unit. So we in case of speed, or in case of car, we don't tell it like rate of the car, but rather some flow is happening. Okay, so heat transfer rate, mass transfer rate. So this rate or fluid transfer rate, this type of mass flow rate, volume flow rate, molar flow rate, this type of rate are defined by this mass of the system per time, or volume of the system for time, or charge generated per time, like this. So rate is very important to know the actual quantity. Right? Then what else is there? We can look at it. So in the first lecture, there is only the, I think, flux. Yes. So this is the flux. Quantity moved versus time per area. And area has to be perpendicular, because the example I have shown. So suppose area is this, right? This is one side of a box, and a fluid is passing through here. So this perpendicular area we are calculating in the flux. So it is the very simple things. I think you already know these things. Okay, let's go into the next part. So rate is also important in the case of reactions. That like at what reaction, at what rate the reaction is happening, like at what rate some product is ready, because these parameters are important, because when you are in an industry and you are designing something, rate, how fast a reaction happens, this is very important to know. That's how you will design everything, right? Even if you're when if your the reactor also is depends upon this rate of the reaction that is happening inside. Okay, so these parameters are very easy to understand with real life examples. Also, you can understand. Okay, so you know that all the time the reaction is happening inside our body. So how fast a reaction happens, how fast an enzyme degrades the carbohydrate, right? So how fast amylase is an enzyme which degrades carbohydrates. Lipase is an enzyme which degrades the fats. So how fast they degrades our food or food parts of the food. So you can calculate from this the concept of rate. Okay. So let's next. There is not much theory in this class, so we'll directly go into the assignment part. So these are the practice assignment given in the NPTEL portal. These are very easy. If you can solve it, please tell me. So what is the value of x? It's very easy, like class 4 mathematics. Can you tell what is the value of x? Yes.
27.
Yeah. So it is just simply 27. Next, find the value of log 10 of 100. Find the value of log 100 base 10. So log 10 100 means, hi,
It
tell.
is also short side.
Uh,
Two correct.
yes, 2. It is option 2. Because it is 10 square and 2 will come up. Next, what is the y-intercept of the line that follows the equation this? What is the y-intercept? So you remember, I think y equals to mx plus c formula. So it is the same.
One.
Yes, it is 1. So let's introduce yourself first. I have not asked you. Uh, yes. Can you introduce yourself?
Yes, ma'am. Manita. I'm studying PhD at SRM University.
Okay, and your department?
Mathematics.
Ah, okay. So why did you join this course, like take this course?
Uh, I chose biometry, that sorry, biosensor. That's why I choose this one.
Okay, okay, sure. So in the first class, there is
In
not
my
much.
PhD,
Yes.
sorry.
Yeah, you are telling something. I just interrupted you.
Oh, yeah, no. In PhD, I chose biosensor. That's why I'm joining this course.
Okay, so you are first year student?
Yes, no, first year.
Okay, okay, good. So as we
Uh,
progress, we'll learn about the like biological aspect of this course more. But in the first class, it is a very basic class, so I have to limit myself for the first week only. So other things we'll get to know as the class progresses. Do you have any particular question? You can anytime ask.
okay, ma'am. Okay, ma'am. Okay, thank you.
Yeah.
Can you suggest any basic books or basic definitions for this related subject?
So basic transport phenomena in biological systems, Sir has, I think, already has talked about this in his first class, right? So I can suggest one book, which is the Transport Phenomena basic book, that is by Bird Stuart Lightfoot. So uh, in this book, you will only get to know about transport phenomena, but not the biological part you will get here. But as if you want to know the transport phenomena, this book is the best one. Okay, so this book, Bert Stuart Lightfoot, this book. So this book is the for the transport phenomena part, but the biological part you have to look for the other books. What sir has suggested in the class. Or also one thing I would like to tell that in PhD, if you are taking a biosensor as your course, so in PhD there is not a single book which you can follow basically. So it's all about the work people have done in this in your field. So better to go through papers, literature surveys, do literature survey properly, and you will learn lots of things from there only because in PhD to find a particular book is difficult. So if you want to learn something basic, then the classical books are there. But for the research purpose, you need to more teach, learn about or study more the literature, basically in your field. That will help you a lot.
Okay, ma'am. Okay, thank you.
Okay, so we'll get back to here, our question. So here, this is a very basic question again.
-1, -5.
Yeah, it is the -1, -5. What is the order of the following ordinary differential equation?
True.
Yeah, it is d2y dx square. So that is second order. Next is the integration.
Fourth one.
Yeah, so I can do it once. So it is x to the power 4 by 4 plus x cubed by 3 into 2. Yeah, plus it is 9 x, right? Constant c, yeah, or plus c. Yeah, it is the fourth one. Next, consider a particle moving along a straight line such that its velocity is inversely proportional to the square of the distance traveled. Formulate a differential equation that explains this relationship. So what it says that a particle moving a straight line, that is velocity is inversely proportional. Velocity is inversely proportional to the square of the distance. That means velocity v is proportional to the distance is r, so it is v proportional to 1 by r square, right? So now, as you know that if velocity is this, so velocity is the distance by time, right? It is also one kind of rate. So velocity is distance, that is r by t, right? So in the differential equation, we'll consider the change of the velocity. So with time, so it is the dr by dt is proportional, is not proportional. It is, we are, as we are writing as equal to, so it is equal to a constant, any constant you can write c by r square, right? So it is option D. So next is the solve 0 to a e to the power x. So integration of e to the power x is e to the power x as it is. So we'll take from 0 to a.
A minus 1 plus c.
Yes, yes. It is e to the power a minus 1 plus option A. Next, which of the following is a solution for this? So we have to solve it. This is a differential equation and we have to solve it, then we will get the final equation. So dy dx equals to minus 8y, right? So dy by y equals to minus 8 dx. So now if you integrate ln y,
Option B.
yes, minus 8. Option B, 1 minute, let me do. Ln y equals to minus 8x plus c.
B.
Why b? Like this is coming as dy by y in.
E from D, y equal to e power minus 8x.
Yes,
plus
it is
c.
option 4. So if you take y now, it will be going to the e to the power minus 8x plus c. So it is option 9, like option 4. Next, the material balance for the system. So in the equation, we have seen that what is the rate. So rate, how it is defined. Suppose this is a system, a simple system, right? So it will calculate its input minus output plus generation minus consumption, that will lead to the total accumulation. Right. So in any system or any process, there is some
Option and third option.
yes. So we'll go like this. So in this case, input is A, right? So A is your input, B is also your input, and outputs are minus C, minus D, and minus E, right? So it is option C, like A plus B equals to C plus D plus E, right? A and B are input and C, D and E are going out. So it is option C. Next. From below, identify the quantity that is not conserved. So it's a very easy thing because we all know that charge is conserved in a system, energy is conserved in a system, momentum is also conserved in a system. They cannot be generated or they cannot be destroyed, right? So it is the force. Right? So force, what is the force? Force is the pressure per unit time. Pressure per unit time. This is the definition of force. Or mass into acceleration is also force, obviously. But in terms of if we want to think to the point of view of rate, so it is the pressure per time. Next. A water tank of 5,000 liter capacity was filled with 2500 liter of untreated water. Normally at this facility, chlorination is done to treat drinking water. The allowable limit of chlorine in drinking water is 4 mg per L. An inexperienced caretaker added chlorine solution without proper measurement, which resulted in elevated levels of chlorine in water, resulting in a final concentration of 8 mg per L. On noticing the mistake done, more untreated water was added at a rate of 160 liter per minute. Calculate the time required to bring the concentration of chlorine to 4 mg per L. So initial value is defined. The initial volume of untreated water was 2500 liter and initial concentration becomes 8 mg per L, right? The allowable limit is 4 mg, but initially it has been done by mistake at 8 mg per liter. Okay. Then the target concentration should be 4 mg per liter, right? And the rate of the added, so it is called the flow rate because it is 160 liter per minute. So as you can see, it is rate, that is liter per volumetric flow rate. So it is liter per minute. Volume of the fluid and per minute. Now we can define that what is the total mass of the chlorine. So how we'll calculate mass? So as we know that concentration or density, these are the mass per volume, right? So mass of chlorine will be concentration of chlorine initially and its volume. That is, concentration is 8 mg per liter and into 2500. So it will be total 20,000 mg, right? So this is the total mass initial. Okay. Now next. So this is the amount of untreated water is present, right? And final volume for the, this is the amount of untreated. So so now at what total volume is required for this 20,000 mg of untreated water, where the concentration of chlorine will be 4 mg per L, right? So now our required C is 4 mg per L, and we know the mass, that is 20,000 mg. So we can calculate the how much volume is required. So this is total V equals to M by C. This is 20,000 by 4. This comes as 5,000 liter, right? So total how much is required? So initially it was filled 2,500, and requirement to undo the mistake is 5,000. So required volume is, just subtract it. So it is 5,000 minus 2,500. It is just the 2,500 liter, right? And the question was asked that choose the value closest. What is the question? Calculate the time required to bring the concentration, right? So now we know the rate, right? We know the volume also. So rate was defined as 160. Rate is, volumetric flow rate is 160 liter per minute. So now how much time is required? So it is the total volume by its total volumetric flow rate, right? So it is 2,500 by 160. So if you have calculator, you can do that on your own. So it is nothing but 2,500. It is nothing but 15.625. So it is the 15.625 minute, almost close to 16 minute you can write, is required to fill it, to fill the chamber, to undo the mistake, right? So the answer is 16 minutes. Okay. Did you understand the problem?
Yes, ma'am.
Yeah. So next question. It is the same chlorinated a strategy was once chlorinated, a strategy was followed to remove the chlorine from water before consumption to reduce its taste. Activated carbon filters were used to filter water which is chlorine treated. A filter of length 7 cm removes chlorine at the rate of 4.6 mg per minute. If two such filters are used in parallel, calculate the concentration of chlorine in the exit stream. Given the rate of inlet and exit stream as 5 liter per minute. So now inlet concentration of chlorine is already given, that is 4 mg per L, and volumetric flow rate is of the stream is 5 liter per minute, right? And the carbon filter can remove the chlorine at the rate of, you can say carbon filter rate is 4.6 mg per minute, and two filter is used, that means it will be 2 into 4.6, that is 9.2 mg per minute is carbon filters rate, right? So total mass flow rate of the chlorine we can calculate. Mass flow rate of the chlorine is Q into C, right? It is 4 into 5, that means 20 mg per minute. This is the inlet quantity of mass flow rate for chlorine. And total removal rate was 9.2 mg per minute, right? Then what is left? So mass, if we subtract it, that means mass out will be 20 minus 9.2, that is 10.8 mg per minute, right? Now it has been asked that calculate the concentration of chlorine in the exit stream. So we know the mass flow rate of the chlorine at the exit stream. We know the stream volumetric flow rate, right? That is also Q. So now we can calculate the concentration of chlorine there. So C will be mass flow rate of the chlorine is that this 10.8, and actual chlorine volumetric flow rate, stream volumetric flow rate is 5 liter per minute. So this is mg per minute and this is liter per minute. It will be how much? 10.8 by 5, that is 2.16. So it will be 2.16 mg per liter. So this is the final exit stream concentration of the chlorine. So it is option B. Next. Now comes the rate equation. So for the system shown below, write the steady state balance for the metabolite A, where these are metabolites and this represents the rate of reactions. Okay. So for the A, we have to consider, what is A? Okay. This portion is A. So you can see that R1 is from E1 or EI, R1 is coming to A, from B, R3 is coming to A, and A is producing C by R5, right?
Option B, Rama.
Yes. So it is
Ma'am,
R.
can you explain 19th slide again?
What?
Can you explain before some again? 19th slide. 19th slide.
19th slide. Okay. Here it is. Okay. So what is happening? Let me tell you. So there is a tank, suppose water is filled and chlorine is mixed, right? So initially the chlorine concentration was 4 mg per liter, right? And we know the stream flow rate, that is 5 liter per minute at the inlet also, and outlet also it is 5 liter per minute. right? This is the chlorine concentration C. This is the uh, inlet flow rate, and this is the outlet flow rate. Okay. And what else is there? Like carbon filter is used, right? Yes, carbon filter is used. Yeah. So carbon filter is used, which rate is 4.6 each. So it is 2 into 4.6, that is 9.2 mg per minute. Right. So initially, what is the mass flow rate? What is the mass flow rate? That is Ci into Qi. That is C is 4 mg per liter into 5 liter per minute. So it is coming as 20 liter will cancel out. It is the mg per minute. It is the initial mass flow rate before adding the carbon filters, right? Now carbon filters are added. That means 9.2 at 9.2 mg per minute, the chlorine is removed from the tank, right? So at the output, like at the outlet stream, you will find that on 20 minus 9.2, that is 10.8 mg per minute chlorine is there, right? At the outlet stream, I am telling. This was the initial concentration, this was the initial mass rate. This was after the carbon filter is used mass rate. So what is left? What much is left? It is the 10.8 mg per minute chlorine rate is available at the outlet, right? So now what they have asked about the concentration of the chlorine at the outlet stream, right? So now we know the mass of it. This is the mass at the outlet stream, and we also know the stream volumetric flow rate at the outlet stream. So now we can calculate at the similar way. We can calculate the outlet stream concentration. So it is C out is the mass flow rate at the out divided by the Q out, right? So simply 10.8 by 5, it will lead to your answer, that is 2.16 mg per liter. So this was the final concentration of the chlorine at the at this tank after using the two carbon filters. Do you get it now?
Yes, ma'am.
Yeah. Yes. Okay. So it is very easy. So R1 is all coming. So R1 is the input rate. R3 is also input rate, and R5 is going out. That is the generation rate or output rate, whatever it is. So it is option B. Next question is the number of rows and columns in a stoichiometric matrix of size m into n denotes what? Okay, so if you remember sir's notes, so it is there.
Option B.
Option B. Yes.
Option B.
It is the n is the number of reactions and n is the number of rates.
Actually, I'm seeing in some place m is equation, n is reactant.
Okay, so let's go to the equation search note. That will be clear. So this is an m by suppose m by n matrix, right? So what it is telling that R is here R is the reaction rate vector and S is the state vector, right? And this has n and n. So what number of columns? Row is n, right? So row are 1, 2, 3, 4, 5, 6, and column is 1, 2, 3, 4, 5, 6 in this case. So first one is the 6 by 6 matrix. Second one is the 6 by 1 matrix, right? So from the matrix rule, we know that 6 by 6 multiplied by 6 by 1 matrix, it will generate. So these two will come at the output, right? These two will come at the output. So it is 6 by 1 matrix. Equations and n is the number of reactants. So here 6 are the number of reactants only. Are 1, 2, 3, 4, 5. Here it is 5, suppose. Okay, here it is 5. Okay, I made a mistake. Whatever it is, this term doesn't matter. So it is 5 by 1. So we are considering in matrix multiplication, two side parts will come. So it is 6 by 1 matrix that are forming finally. So what is it? The number of rows in rows and columns in a stoichiometric matrix of size n into n denotes what? Stoichiometric matrix is your this, right? These are the rate matrix and these are the stoichiometric matrix. So here n is the number of reactants. You can see here, right? So these are all your reactants, right? S0 is, if you go back to the problem, yes, it is all. It can be said actually both. These are also reactants also and state variables also, right? So, it is very confusing. 1 minute. So n is the rate equations. That's for sure. Because you can see here that from where this so this R0, R1, these are rate equations, right? So this is forming this rate column also, and this column has one column. Like this vector has this matrix has one column. So n is your number of rate equation, and similarly m will be the reactants, because here you can see that A0, As are the reactants in the system in the diagram you have seen, and R1, R0, R2, R3, R4, these are the reaction rates. So definitely n is the number of reaction rate equations and m will be the number of reactants. So it is option B only. Is it convincing? So is this convincing? Right? So n is the number of rate equations and m are the number of reactants. Okay, next question. A bacterial culture is maintained in a conical flask. The flask is kept in a shaker incubator, which swirls the contents to ensure proper mixing. However, while performing the experiment, the RPM was wrongly fixed and the flasks were incubated under unfavorable conditions, leading to non-uniformity in culture conditions within the flask. If the interest is in representing the variation in the concentration of the extracellular products produced by the bacteria at different spatial points in a flask with time, which among the following is the best choice? You think and tell me. So, what is this? What is this total derivative? So, as you have gone through the lecture of SIR, you probably know the total derivative is the, suppose we are doing it for a parameter C, right? It is dC. First, we are taking the differential of, suppose, okay, let's start fresh. Suppose C is a function of x, y, z, and t, right? So now if we take the differential of C, so it will be del C del x equals dx, okay, at constant y, z, and t, plus del C del y into dy at constant, sorry, this here, at constant x, z, and t. Then del C del z into dz at the constant x, y, and t, plus del C del t into dt at constant x, y, z, right? So now, if we write, we can write like this, right? dc dt. So it will be del C del x dx dt plus del C del y dy dt plus del C del z dz dt plus del C del t. So this is the whole thing, right? So this is called your total derivative. Okay, this is the total derivative. What about partial derivative? So partial derivative is the simple terms, right? So del C del X at constant y, z, t, you can call it partial derivative with respect to s. Similarly, del C del t is partial derivative with respect to time like this. Okay. And what was another one? Another one was the substantial derivative. So substantial derivative will also come from here. Substantial derivative. It will come from here. It is the dc dt. So as you know, from the total derivative, you know that dx dt, it is nothing but your velocity, right? Distance by time, right? This is also a rate. So this is the, if you think like this, that this is the x directional change with respect to time. So it is also defined as u. This is the x directional velocity. dy dt can be defined change in distance with respect, change in distance in the y direction with respect to time. So it is v. And this is change in direction in z with respect to time is z, uvw. So w is the z directional velocity, v is the y directional velocity, u is the x directional velocity. So if we combine and write, what can we write? So it is the del c del t plus u del c del x plus v del c del y plus w del c del z, right? So if you write like this, dc dt, if you write in vector form, what will be? It is del c del t plus divergence like divergence of grad c into v. This is a vector form, or you can write the opposite way also, v dot grad c, whatever. Oh, it is better, v dot grad c, right? V is the vector, velocity vector, and grad c is the grad vector, right? Differential of it. Okay. So this is the substantial. So what is the meaning of it? So what is said here? A bacterial culture is maintained in a conical flask. The flask is kept in a shaker incubator which swirls the contents to ensure proper mixing. However, while performing the experiment, the RPM was wrongly fixed and the flasks were incubated under unfavorable conditions, leading to non-uniformity in culture conditions within the flask. If the interest is in representing the variation in the concentration of the extracellular products produced by the bacteria at different spatial points. That means at different spatial points, it is said, right? At different spatial points, the concentration of the extracellular product is defined. That means they are not related to one another. They are not dependent to one another. So the variation in the concentration will be independent from one spatial point with time, one spatial point to another spatial point. So when there is no dependency with the other variables, that is called the partial derivative. Okay, so it is the partial derivative. I think you got it. Next. A bacterial culture was maintained in a continuous stirred tank reactor under steady state in constant volume process. Right? Volume is constant. Identify from below the equation that best describes the change in concentration of product with time in the system, given that there is no feedback to the system via input stream, and that the products are constantly removed through the exit stream. Okay, RGP is that means, suppose this is something A and output is constantly going to the exit stream. Fp is the mole flow rate of product in the exit stream. FO is the mole flow rate of the inlet stream. V is the volume of the reactor. So rate, we have said earlier that rate is the defined. So input rate. So input rate minus output rate plus generation rate plus minus consumption rate. These total, it leads to accumulation. Okay. So it is said that there is no feedback to the system via input stream. Okay. So input stream is 0. And that the products are constantly removed through the exit stream. Okay. Now that means output is there, right? So rate of So Fp is the mole flow rate of the product in the exit stream. So it is the output rate. So it is minus Fp, right? Is the generation? So there is generation rate is product is given, right? That is RGP and volume of the reactor is V. So as you know, Fp is the flow rate, mole flow rate, right? Mole flow rate, that means mole per time, right? Rate is the how these two units are same. That is what I'm saying. So RGP is the rate is the volume no volume of the failure is L, right? Volume of the reactor is defined as L. And this rate is defined as, suppose uh, some mass is defined, right? by L. That means you can think it of as mole also per unit area volume and time. So, and there is also no mention of accumulation. So it is also 0. So what it comes? It comes as RGPV equals to FP. Okay, so this is your answer. First, option A. Next. The number of rows and columns in a stoichiometric matrix is already defined, already told. It is the M is the number of reactants and N is the rate equation. Next. In a stoichiometric matrix of size n cross n denotes the number of columns is the reaction rate, right? It is the rate reactions. That's what I said earlier also, right? Next. As a pre-treatment strategy, activated carbon filters are used to remove fluoride from drinking water through the process of adsorption. The allowable level of fluoride in water is 1.5 mg per L. The input water stream contains 3 mg per L fluoride. Water is supplied at a rate of 100 liters per minute to this pre-treatment facility. Every gram of activated carbon in the filter can remove 0.06 mg of fluoride in a minute. One such filter contains 1000 grams of activated carbon. Multiple filters are placed in parallel in this pre-treatment step. Assuming that the adsorption efficiency is not affected by changes in the concentration of fluoride in water, find the minimum number of such filters to be used to bring the fluoride level under 1.5 mg per liter in the existence. So it is almost the same problem we have done earlier with chlorine, but it is a little bit different way. So similarly, if we can consider, so inlet concentration of the fluoride is 3 mg per liter, and allowable concentration or target concentration you can write as 1.5 mg per liter, right? Volumetric flow rate at the inlet is of the stream or water is 100 liter per minute, right? So now if we subtract one CO minus CI, so that means this amount of concentration of fluoride needs to be reduced or removed, right? So with this flows, so target removal rate will be so this is your water stream flow rate, this is the concentration to be removed. So target rate will be Q into difference of C delta C. So if you multiply 100 liter per minute into 1.5, it will give you 150 mg per minute. Okay. This is your target removal rate. And capacity per filter is defined as, for carbon filter, 0.06 mg per minute, right? And capacity per filter is, one such filter contains 1000 gram of activated carbon. That means total capacity will be, like a single filter can remove 0.06 mg per minute of fluoride at the rate, and this activated carbon has such 1000 filters. So total capacity will be 1000 into 0.06, that is 60 mg per minute rate, mass flow rate. Okay. So now number of filter is needed as, so total removal rate is 150 and we have 60, it will be 2.5. So 2.5 filters are required. Okay. So you can write it close to 3. Okay. Option 3. Next. In a house, a water tank of 2000 liter capacity was filled with 500 liter of untreated water. Here chlorination is done to treat drinking water. The allowable limit of chlorine in drinking water is 4 mg per L. Due to inexperience, chlorine solution was added without proper measurement, which resulted in elevated levels of chlorine in waters, resulting in a final concentration of 8 mg per liter. On noticing the mistake, more untreated water was added at 60 liter per minute. Calculate the required to bring the concentration to chlorine. So it is also kind of the similar problem we have seen so far in the first. So still do it. So initial volume was given 500 liter. Okay. Initial concentration was given of chlorine is 8 mg per liter. The final concentration is, sorry, this is out. This is your 4 mg per liter. Okay. So total flow rate or flow rate of the water added is also given. So Q is defined as 60 L per minute. So total chlorine mass at the inlet was, Vi into Ci, that is 500 liter into 8 mg per liter. So 4000 milligram. Okay. So this is the total chlorine mass of the total chlorine present, and final output is 4 mg. So its volume should be 4000 mg by 4 mg per ml. So it is 1000 liter. Okay. So 1000 liter will be the final stream concentration, final volume, stream volume, and coil tank volume. Initially 500 liter was given, so it will be the delta V will be 1000 minus 500 is equals to 500 liter water needs to add, and at what rate it can be added? With the, we have to define in the and how much time it will take, we have to divide this by the rate, that is 60 liter per minute. So it will be 8.33 minutes, which is close to 8 minutes. Okay. So it is the option A. Next. For the system shown below, write a steady state equation, write a steady state balance for the metabolite M1, and these are metabolites, and Rn represents the rate of the NH reaction. Okay. So for M1, right? So here it is M1. So you can see input is happening. So R1. Also there is another input. That is R4, and one output or consumption, that is R3. Okay, so it is R1 minus R3 plus R4. It is option C. Next, sorry, it is dm1 dt. Okay, it is also always the rate of accumulation. Next, there is also a similar type of problem we did. Let's do it again. A bacterial culture was maintained in a continuous stirred tank reactor under steady state in a constant volume process. Identify from below the equation that best describes the change in concentration of substrate with time in the system, given that the substrate is supplied the system through an inlet stream with mole flow rate Fi. Okay, there is no feedback to the system and the products are constantly removed. Okay, so inlet stream mole flow rate is defined. So there is an inlet Fi. The products are constantly removed with the exit stream. RGP is the rate of generation of product. FCS is the rate of consumption of substrate. FP is the mole flow rate of product in the exit stream. Fs is the mole flow rate of unconverted substrate in the exit stream. V is the volume of the bioreactor broth in mole per second. The unit of mole per liter per second. Yes. So the system is talked about like this. Substrate is supplied to the system through an inlet stream with mole flow rate Fi. Oh, that is different. That means substrate is supplied, but that means substrate is consumed. Consumption is happening here. Substrate is itself supplied to the system through an inlet stream. That means it has an inlet portion which is defined by Fi, right? It has a consumption rate of the substrate. So Fi consumption is Fi minus RCS into V, and it also has some unconverted substrate in the exit stream that is going out, that is minus Fs equals to 0. Okay, So it will be RCSV plus Fs equals to Fi, which is option C. Okay, next. So you have to always look into the parameter, like what is the input, what is the output, what is generating, what is consumption, and what is the accumulation. Like here accumulation is again 0. Next, under what condition is the continuum approach valid for analyzing a gas system, and what happens when the system transitions into the discrete region? Valid when the mean free path is much larger than the characteristic length, density fluctuates wildly in the discrete phase. This option is wrong because we have defined that continuum for continuum approach, characteristic length has to be greater than the mean free path. Valid when a large number of unitary particles exist per unit volume and distance traveled before collision is much smaller than the mean free path. Density fluctuates wildly in the discrete phase. Option C, valid only at absolute zero temperature. No fluctuation occurs in either regime. Valid when the system is non-viscous. Particles do not experience collisions in discrete phase. So option B is the correct one. Next. In the context of studying fish concentration in the ocean with a motorboat, which derivative represents the time derivative following the motion or substantial derivative? In the context of studying fish concentration in the ocean with a motorboat, which derivative represents the time derivative following the motion? That means the time derivative following the motion or the substantial derivative. The local time derivative, the first option is holding positions coordinates fixed. No, this is wrong. Total time derivative tracking the boat's specific velocity components. It is also wrong. C is the local time derivative combined with the convective transport term due to fluid velocity vector. So it is the upside. This is the substantial derivative expression also. Right? According to the introductory lectures on engineering curricula, which statement best characterizes the primary operational distinction between academia and industry? Academia focuses exclusively on short-term product delivery, while industry focuses on 50-year theoretical benchmark. Academia functions as an ideal benchmark for long-term training and fundamental principles, whereas industry is rooted in focused short-term day-to-day operations. There is no functional difference between their goals. Both operate strictly on quarterly economic cycles. Industry rejects non-ideality entirely, while academia relies heavily on non-ideal manufacturing methods. So option B is correct if you have gone through the first lecture. Okay? So from this point, you can also understand that why academia and industry both are important for a student to grow in life, right? And like that way, you can decide your future, that where you want to contribute. Is it in academia or is it in industry? Okay, next. Why does engineering analysis heavily prioritizes rates? Example, mass or moles per unit time or over static amounts. So rates are dimensionless quantities that eliminate unit conversion errors, which is wrong. Amounts cannot be measured experimentally in any biological system, which is, I think, also wrong. Because to calculate amount, you need rate, right? It is self-contradictory. Dynamic systems like biological cells or continuous bioreactors change with time, making rate equations essential for setting up algebraic or differential balances. Conservation laws only apply to rates and are mathematically invalid for absolute masses. So option C is the true, because at every point of our body, the reaction, the concentration, the mass changes. It changes with space and also with time, right? So that's why rate is important. Next, angular mean free path is 0.2 millimeter, and the characteristic length scale, therefore thickness is 2 millimeter based on the Knudsen number, which is lambda by L, where regime does this which regime does this flow fall under, and can the standard Navier-Stokes continuum equations be safely applied directly without modification? So Knudsen number, if we calculate Knudsen number here, it is lambda by L, that means 0.2 by 2, it is 0.1. Okay. So continuum regime where Knudsen number is less than 0.01, standard continuum equations apply perfectly. No. Slit flow regime is this standard continuum equation breakdown entirely. This is also wrong. Transition or slit flow regime, it is 0.1 to 10. Standard continuum equations with no slip boundary conditions begin to fail, and slip corrections or statistical mechanics approaches are required. So its value is 0.1, right? So it falls in this transitional or slip flow regime. Standard continuum equations with no slip boundary conditions begin to fail, and slip corrections or statistical mechanics approaches are required. So below 0.01 continuum flow equations apply, where I am telling that L is greater than lambda, right? It is option C. Next. A temperature field in a fluid flow channel is described by the steady spatial coordinate function T equals to 3x square plus 2y. If a fluid particle moves through this field with a velocity v at a location where x equals to 1 and y equals to 3 meter, what is the total rate of change of temperature experienced by the movie? Okay. So here we will be applying the substantial derivative formula. So if you know dt equals to del t small t plus u del t del x plus v del t del y, right? Yeah. So, but this is not given anything. So this is 0. And from the equation we know that del t del x will be 6x, at x equals to 1 it will be 6, and del t del y will be 2, right? So total rate of change of temperature experienced by the moving particle. So del t dt will be just simply u into del t. So you have a value, right? U is 2. Del t del x is 6. Plus v is 4 and del t del y is also 2. So this is 12 plus 8 equals to 20. So answer is 20 Kelvin per second. But this answer is not given. Okay, so don't write the answer. These are wrong. So the answer is 20 Kelvin per second. Okay, next. And probably the last one. A well mixed stirred tank reactor of a constant volume contains an aqueous salt solution. Liquid enters at a volumetric flow rate of 0.05 meter cube per minute with a salt concentration of 20 gram per meter cube and leaves at an identical volumetric flow rate to maintain constant volume. Okay. If the initial salt concentration in the tank is this, what is the initial rate of accumulation of salt in the tank at time t equals to 0? So mass accumulation we have studied, right? Input minus output equals to accumulation, right? So input is defined as V in, C in minus V out into C out equals to accumulation is dm dt, right? So at t equals to 0, when at time started, the initial V in was 0.05 and initial concentration was 20 gram per meter cube, right? Minus outlet also have same volumetric flow rate, which is 0.05. It is 10, right? So this leads to dm dt. So what will happen? 0.05 into 20 means 1 minus 0.05 equals to 0.5 gram per minute is the answer. This option A. Okay. So I think you have understood this class. This class is all about very basic concept of rate equations, flux, and mass flow rate, volumetric flow rate, and concentration like this. So all this can be correlated with the biological system, which is constantly happening in our body if you think carefully. So please go through the problems. I have done several problems which will be helping you to solve this week's assignment. Okay. So still, if you have any doubt, please contact me, and we'll be meeting on the same time next week for the second session. Okay. Till then, goodbye. Thank you. Thank you for joining.